So I'm picking up where I left off on this video with respect to how to process, visualize modal acquisition and modal analysis data. From the previous video, I may remember we were trying to fix or change the axis here, and I was getting myself in trouble because the window that actually opens when I double click this number here, it appeared on the other screen and was tucked in behind my recording dock. So if I drag it back into this display, you can see that I can very conveniently now zoom in on those data. So we've changed the axis limits essentially. If I right click on here, there are some other options, various options, and depending upon exactly how I right click on here, I get, or left click, double click, I get different options. Here you can see the limits for the axis. Currently they're fixed. They were free. It was determining the limits based on the data that was displayed in this preview mode window. So by double clicking and specifying this upper limit, I've effectively changed the limits to fixed. I can change format here for frequency data, obviously from linear to octave and decade. We've seen previously, in fact in preview mode in a Bode plot, we've seen previously how to change log scale here. I've put automatic cursors on before. I can add single cursors and move them around manually. I've shown how to put a cursor legend in there. With a double cursor, I can, for example, put a calculation in there. There are many options for how you can interrogate the data in this display, and using all of them is beyond the scope of this video tutorial. I'll remove that cursor. We're back to essentially where we were. I want to spend some time now using the capability in this area here, and particularly the columns and filtering of columns, to be able to manipulate what information I have available to me in here to be selected and displayed in preview mode. I'm looking to try to look at my coherence function as an FRFs that have been previously recorded. Remember, I had one reference, but I've got multiple response measurements. These response measurements I'm not interested in for the sake of this exercise. I am interested in this FRF, and I'm not really interested in this FRF. This is the driving point FRF, which won't change at any time. These are the ones I want to use for modal analysis. These I'm not interested in. Now, if I go back to this section heading, I can select multiple runs. Remember, I said I had 6 runs for the scenario where I have no base motion vibration. This is my first modal analysis. When those are highlighted, I can use this list all blocks function up here to essentially put all of the functions within each of the folders within those 6 runs into this display. Now, there are auto powers, there are spectra, there are coherence functions, FRFs, and so on. Remember, I don't want all of the FRFs. Some of them I'm not interested in. So I'm going to use some filtering time data here as well, of course, using columns to manipulate what's displayed. So here I can go into the select columns, and there are lots of options in here, but normally I just want to go straight to the Testlab option. Now, the main options within here are things like the run, the section, the project. For example, I can change use the run name as being something which I can add in as a column. Now, it's remembered because I previously checked these and took these out, the other things that I'm interested in, and when I've put those in, it's put some other things in here as well because they were previously highlighted. Now back to here. So if you didn't know that previously, I can apply that run name. Now those runs are displayed here, and I can't do it now because I'm still selecting. I'll be able to use these filters to only show, for example, runs 1 to 6. The other thing that potentially is useful is the block. Now that's something about the block is essentially the data itself, and so if the degree of freedom ID might be something that's useful to filter on. I might also want to, for example, filter on the reference degree of freedom ID. I could add that in, the reference being the force transducer in this case. And the other thing that I often use in here is the function class itself. So if I want to only display, staying in the block type, the function class is further up this list. So if I want to display just FRF or coherence or time or something else, then I can select this one here. So put that one in there. Okay, that now you see I've got these 3 extra columns, and these checkboxes here within the filtering allow me to eliminate, for example, all but runs 1 to 6 to begin with. I'm not interested for the moment in runs 7 to 12. That was for a slightly different measurement. If I click here with a left click, it will sort by run. If I click here, it'll sort by name alphabetically in descending order. And over here I can choose to filter on, for example, just coherence and FRFs. Now my list of items available to me is getting a lot shorter. Remember, I'm only interested in the LDV measurement, so similarly I'll deselect those and turn that one on. Now I've just got 12 functions. I've got the coherence functions and the FRFs for the measurements of interest to me, the LDV measurements with respect to the force transducer that was at the end of the stinger. I could go back here, remember, and I can include the reference .id, but it's going to be the same for all of these. I can also reorganize these here. So normally we'd have response.id, reference.id, so now we get an extra column. I can adjust the width of the columns for the sake of being able to see everything in the view. I can adjust the width of this one as well, make most use of the real estate that I have available to me. Remember, I'm using the Bode plot and the front back here in preview mode, so if I select these 6 coherence functions, then they'll be added in very conveniently here. Remember, from my experiment, I've only been using excitation up to 100 Hertz. So I'm just changing so everything above 100 Hertz, this is 100 Hertz here, this is 520 at the end, so 100, 2, 3, 4, 520. I wasn't exciting the structure above 100 Hertz, so there's no interest in these values. I was acquiring data at up to 512 Hertz, but I'm not interested above 100 Hertz. And you can see the coherence functions are pretty good. We need good coherence is 1 across the frequency range, but particularly at the frequencies that we're interested in, i.e. where the resonances are. And from these FRF measurements, which I can display in this Bode plot instead, I know that this frequency 16.13 Hertz is my first frequency of interest. That's where I get my first resonance, and the second frequency of interest is towards the upper frequency limit. For me, it's not particularly, I'd prefer it for that to be a bit lower, that frequency, prefer for my beam to be a bit longer, and then I'd have a lower frequency. But let's just focus on this frequency here, which we can do. So at 16 Hertz, if I go back to the front back, you'll notice that when I move, because I'm in preview mode, these data change according to what's highlighted. I can turn off preview mode here, and I can remove all curves. That was all cursors, my bad. Remove all curves, and then in the Bode plot I can drag and drop those curves, so they're now going to be permanently in this plot and it's not in preview mode. Right click here, add an automatic cursor, a peak cursor, which should go back to this frequency 16.3 and tell me the values of the vibration, or of the FRF, in meters per second per Newton at that frequency, and the phases. Now this information, if I was to change this information from log to real and imaginary here, then of course the imaginary parts, the values of these responses at the imaginary parts and the real parts, tell me basically the mode shape of the structure. And in the case of velocity measurements, it's these values here that tell me the mode shape, and they increase from 0.1, which should be the red curve, the closest to the beam, to 0.36 to 0.68 as we move along the length of the beam. That's called quadrature peak picking, and that's the process with which I can essentially do a modal analysis. If I go back to this Bode plot here, let's remove all the curves from here, which I'm a little bit, why can I not remove all curves in this one? I can do it from here. So Select all curves. I'm still in preview mode. I apologize. Now I can drag and drop these coherence functions in and add them. I can put that single cursor back in at that'll go in as a default at 50 Hertz, put it at 16.13, and so the coherence function isn't particularly good at 16.13 Hertz. There's a bit of a drop there at that frequency, so we need to take care with paying too much attention to these data. There are some issues with the way I collected these measurements, and so this is not about the quality of these data, this video. It's about how to use Simcenter to interrogate the quality of data, and here we can see that there are some problems with those values at 16.13 Hertz. So this would be telling me to recollect this set of measurement data. The problems I have with these data I can be explicit about, and that is that I used a force transducer here that should have been IEPE coupled, but unfortunately it wasn't IEPE coupled. So if I have a look at the properties from the run, I need to turn off these various filters. So show all. Now these archived settings in here, I can see the channel setup that I used for this measurement campaign. There's a lot of information on the channel setup. It's currently spread across 2 screens, so I'm just trying to resize it so that it fits within the window that I'm presenting or recording this presentation in. So let's put that in this window, and so here you can see these are the various channels that I had. Ignore the tachos. This is from the different module. These are the built-in tachos. There's the LDV channel, the 3 correction accelerometers. These 2 channels were not used. This was the impedance head accelerometer measurement and the impedance head force measurement. Now there's lots of information about these measurements. That was ticked on as a reference. That's correct. The units were specified correctly. The specified quantities were good. This was the sensitivity that I specified, both for the accelerometer and the force transducer. This was the range that was used. And scrolling along, you can see that where I am able to specify the input mode, here this should have been specified as IEPE or ICP. This would have been providing the power then for the inbuilt signal conditioning electronics on the transducer, the integrated electronic piezoelectric conditioning. But unfortunately these had been changed to AEC, and because we were collecting these data in a bit of a rush when we did so, we neglected to change those input mode settings to IEPE to provide the power that was required to the accelerometer. So even though the accelerometer still makes a measurement of sorts, you know, and we can see the resonant frequencies in the FRFs, they are not, the noise here, the extra noise is coming about as a result of the fact that the signal conditioning was poor. The extra noise on the coherence function, for example, in this area, and particularly at that resonant frequency, would have been avoided if we'd had the proper IEPE signal conditioning. So we will need to make those measurements again. The purpose of this exercise and this video, however, was to use these filtering capabilities, demonstrate the list all blocks, spend some more time demonstrating preview mode, using cursors, using cursor legends and so on. We have many options in here. The curve legend, I can change this information that looks similar to what we were looking at before. So again, for example, if I want to know what run these data come from, I can show that in the cursor legend on the plot. So the run, in fact the run name is highlighted by default. Apply this one, and the run names are nicely presented alongside the colors, so I know which coherence function comes from which point. The DOF ID I didn't specify when we collected these data. I would do that subsequently for the modal analysis, purposes of modal analysis. That's something else that we should change when we acquire these data. And one more point, so once I've prepared my plots, it's obviously quite useful to be able to export those plots for the purposes of presenting these data. So that's something that we might like to do, bring the legend out of the way, and there are various options for that. So I can copy it as a meta file. I'd probably recommend not copying it as a bitmap. That's just a dumb image essentially, but it's an option. A more interesting option is to use active pictures. So there's a free plugin available from Siemens Simcenter Testlab, which allows us to have this plot with these sorts of functionalities like an active cursor, the ability to move the legends around and paste those with the data embedded, which is preferable. It'll make for a bigger file than you would otherwise end up with. But it's better if you use an embedded data format for the for this than, for example, a linked data one in case you move the project file after the fact and then the data is no longer available. So in here we can paste this image as a dummy image or as a picture. If we had the active pictures plugin available from Siemens Simcenter installed, this would become a live image in our PowerPoint presentation, which we can click like this and move those cursors around within that presentation. So that's something to have a look at subsequently. I'm not going to demonstrate that in this video. In fact, I need to stop the video at this point because it's getting rather long, and I hope it's been useful to you. Enjoy your time working and processing data in Siemens Simcenter. Good luck. Thank you.